Hello everyone, we are going to do the next set of questions from series.
Problem numbers 64 to 76. So these are the questions. Now let's see the solutions of all this.
So we'll start with question number 64. Alright, okay, so C is a real number and a sequence is defined as un is equal to 1 plus e by n to the power n square by 3 minus 1 by n to the power n. Okay, then the values of C for which the series converges. Okay, so uh, so we are supposed to find the values of C where this series sigma un converges, right? Okay, so the first condition is that if this series converges, then the limit of the sequence must be equal to 0, right? So we are going to apply that condition first. Anyway, that's a necessary condition. So anyway, that should be satisfied. All right. So first we take just the limit of the sequence, and we know we need to get this one 0. Okay, so it's 1 plus e by n to the power n square by 3 minus 1 by n to the power n, and we write this n square as something all to the power n. I mean n times n is n square, right? And here you can take out this 3, so 3 to the power n minus times 1 minus 1 by 3 by n, and as n goes to infinity, this is a standard limit, and this is e to the power c, this one, right? So that is e to the power c, and this is e to the power minus 1 by 3 times 3 to the power n. Okay, still there is a term like e to the power c by 3 the whole to the power n, right? E to the power c by 3 all to the power n, such a term is also there. Okay, so yeah, so what happens is, to make this limit is equal to 0, this e to the power c by 3, I mean actually we have here e to the power c by 3 all to the power n, right? And a constant like e to the power minus 1 by 3, and this has to be 0 as n goes to infinity. So what happens is that, this must be 3. Yeah, this must be less than 1, then only this exponential term goes to 0, right? So this must be less than 1, that is what we need. So e to the power c by 3 is less than 1. Okay, from which we obtain the condition e to the power c is less than 3, and you take the logarithm on both sides, so you will get c is less than ln of 3. Okay, so that is the condition we have. C is less than ln of 3. Anyway, that's a necessary condition. So so all the other conditions must be avoided, right? And that is the right way. Okay, so log 3 is less than c, I mean c should not be anyway greater than log 3, so this is wrong, and this is wrong, and this is wrong, and thereby this is correct. Okay, all right. And 65, we have a sequence here. Un is equal to 8n plus 3 by 3n minus 1 the whole square times 3n plus 2 the whole square. See, here we are supposed to calculate the sum, uh, not enough to check the convergence. Okay, so you know check whether this is a geometric series. No, so the next step is, go for a telescopic sum, and here that is possible. Actually, you try to split the denominator. I mean, you try to write this as a sum or difference of two terms. Okay, so and that is easy because only such questions will be asked. Okay, so just write 3n by 3n minus 1 the whole square in the denominator, and 3n plus 2 the whole square in the denominator, something like this. All right, and yeah, this is what you will get when you simplify. You will get 3n plus 1 the whole square here minus No, 3n minus 1 the whole square. When you simplify, you will get 18n plus 3, and that is what is here. Okay, and substitute n is equal to 1, n is equal to 2, and so on. Okay, so when n is equal to 1, this is what you will get, n is equal to 2, this is what you will get, and finally nth term is this. Okay, and we can see that positive negative terms will get cancelled in a diagonal way, and it remains, when you add up all these terms, you will get the partial sum, and that is nothing but 1 by 2 square minus, that means it remains only the first term and the last term. 1 by 2 square minus 1 by 3n plus 2 the whole square. So that is Sn. So it's enough to take the limit as n goes to infinity. So the answer is going to be 1 by 4. Alright. Yeah. Yeah, that's it. Hope you understand that. Okay, so telescopic sum, that's idea. And 66. Two sequences are given, an and bn. Need to check the corresponding series converges or diverges. Consider the first one, sigma e to the power minus 2n sin n. That's really easy because we because sin n, we cannot say that it will take always positive values, but there's a possibility that it takes negative values too. Okay, so this is not a positive time series. So in such case, always better to check first the absolute convergence. So take the modulus of the nth time. Okay, and that's always as there is a upper bound for sin n, that is 1. So this is always less than or equal to e to the power minus 2n, and the right hand side series sigma e to the power minus 2n is actually, this is what we have, sigma e to the power minus 2 all to the power n, and this is the r value there, and r is the common ratio which is less than 1. So this is a geometric series actually. So that is convergent because this one is a geometric series, geometric series. Okay, therefore this is convergent. Okay, so it's absolute convergent. The absolute series is convergent by the direct comparison test. Okay, so the series converges absolutely in the sense that series converges. So sigma an converges. Okay, now look at the second one, sigma bn e to the power minus n square sin n the whole square. Right, here again you can write it like the same idea. Sin n has a bound, since this one is the whole square, right? So actually this one is a positive time sequence, no need to take the modulus here. But still sin n is having an upper limit which is 1, so it's always less than or equal to n square times e to the power minus n. I write that e to the power minus in the denominator, and here we have e to the power n. And now see, we have two series, this one and this one, right? So if the series on the right hand side is convergent, then the left hand side also converges as well. And we need to check for the right hand side. So use the what, the ratio test there. So un, you take this as un. Okay, this is un, and apply ratio test un plus 1 by un, and when you simplify all these things, you will get 1 by e. Okay, 1 by e, and that is less than 1. So the so by ratio test, the series on the right hand side is convergent. Therefore, by direct comparison test, the series on the left hand side is also convergent. That means both of these series are convergent. Alright, both sigma n and sigma bn converge. Well, yeah, that's it. Okay, now we go for 67. A sequence is defined piecewise. That means for even numbers, we have the sequence n 2 to the power minus n, and for minus 3 to the power minus n, and for odd integers we have n e to the power minus 2n, and that is what the sequence is. Okay, so we need to check the convergence of this sequence. Okay, and convergence of the sequence mod a n all to the power 1 by n, and the convergence of series a n, and the absolute convergence. So all these things must be checked. All right, so first let's see the limit. Okay, limit of a n. Okay, so we think it in such a way that you take all the even numbers, and as n goes to infinity through even numbers. Okay, so this is what the sequence that you need to take: minus 1 by 3 to the power 2n. As n goes to infinity, that goes to 0. All right. Similarly, you consider the other one also: n by 2 to the power n. So if n goes to 0 through all the odd numbers, then what happens is that this is again, see, we have seen a comparison type of thing when to find the limit. We have a linear polynomial in the numerator, and we have an exponential term in the denominator. So the exponential function goes to infinity first, so the denominator dominates over the numerator. So therefore the denominator will be infinity first. So what happens is that also converges to 0, right? And one more thing, now we have taken two different paths to go to infinity, right? uh, and okay, we got the same limit, and that is the only limit here. As this one is a sequence, you cannot find any, and this is not alternative, nothing, kind of thing. uh, it's an alternating sequence, right? Or positive negative, yeah, it's an alternating sequence, but this is the only limit point that we have, 0. So we can say that the limit n is equal to 0. All right. Okay, and you take okay, so the first one is right. The sequence n converges, and that converges to 0. Okay, now sequence mod n all to the power 1 by n. Mod n all to the power 1 by n. So first you take the case of the odd numbers, okay, and you take mod n, all to the power 1 by n. So this is what you will get. That means when you simplify, you will get it like n 2 to the power minus n all to the power 1 by n. This is what you need to take. So n to the power 1 by n, and these n will be cancelled, and you will get 1 by 2. Okay, and this one is a standard limit, right? N to the power 1 by n. As n goes to infinity, you will get 1. So the answer is going to be 1 by 2. 1 by 2. Okay, but the other one, as n goes to infinity through even numbers, then we have you take the mode of that, so this negative will be gone. So 1 by 3 to the power n all divided by n. So you'll get only 1 by 3, so the limit is 1 by 3. So you have two different limits. One is 1 by 2 and other one is 1 by 3, right? So for a sequence, we have two limits. So we can find the limit supremum and limit superior and limit inferior, but that sequence does not converge, right? As there is two limits. So B is wrong. Now check for the convergence of the series. What is sigma mod an? Okay, actually here even and odd terms we have together, right? So actually this is what we need to do. You know what? Like yeah. Series means you have to add up all the times, right? You have to add up all the times, and I have taken all the even times together. Then I got this one, sigma n by 2 to the power n. Similarly, as I take all the even times together, then I get sigma 1 by 3 to the power n. That's it. Modulus of n. So we are taking only positive time series, right? Or we are going for absolute convergence. We are going for absolute convergence. Okay. So look at the first term as sigma n by 2 to the power n. Okay, so as n is an odd number, right? So I write that in another way. Usually we write odd numbers using 2n minus 1, right? So n is odd means I can replace this n by some 2m minus 1 kind of thing. So I write it like the same time. I can write it like sigma n is equal to 1 to infinity 2n minus 1 by 2 to the power 2n minus 1. Actually, you will get the same time. As n is equal to 1, you will get 1 by 2. As n is equal to 2, you will get you know uh, 3 by 2 to the power 3. Okay, that means I replace this old by something like 2n minus 1. That's it. Because if I write 2n minus 1, always I will get odd numbers. Okay, so I've rewritten the sequence like this. Similarly for even times also. Okay, I just replace n by 2n, and then I make n is equal to 1 to infinity. Okay, now see, so the given series is actually the sum of two different series, right? The given series actually is the sum of two different series as n goes to infinity. So these are two different series, sum of two different series. So it's enough to check whether these two are convergent or not. Okay, see, the second one is a geometric series, this one is geometric series, and with a common ratio 1 by 9 which is less than 1, so this one is convergent. Okay, and for this one 2n minus 1 by 2 to the power 2n minus 1, I'm not going to do this one, but you can apply for a ratio test here. uh, we have done test like this actually. So apply ratio test, and you can see that that series also converges. All right, so this one also converges. So these two series converge. That means, this sigma mod n also convergent. Okay, so it's absolute conversion, right? When you take the modulus and you find the sum, uh, that is absolute conversion. So if the series is absolute convergent, definitely the series is convergent. Okay, so it's absolute convergent as well as convergent. So the series is absolute convergent and it is convergent. So A, C, D are right. A, C, D are right. That's 67. All right, and in 67, we have log of 1 plus 1 by n by n to the power a. Okay, so the convergence of the series based on a. So for what values of a the series converges? That's our question, right? So it's log 1 plus 1 by n, right? Okay, so when just when you see that it's log 1 plus 1 by n, expand that. We have the formula for that, Maclaurin series expansion. Okay, and there is a 1 by n common. Take it out. So 1 by n to the power a plus 1. Okay, and you try to apply the limit comparison test by taking this one as sigma bn. So sigma bn is equal to sigma 1 by n to the power a plus 1, right? And you, when you divide, actually you will get the limit as 1. So definitely we can apply the what limit comparison test. Okay, so it converges if sigma bn also converges, right? Sigma, if sigma bn converges, definitely we can say that sigma n also converges. Okay, so what is the condition for sigma bn to be convergent? Actually it's a p series, right? So a plus 1 must be greater than 1, and that must be the condition. Sigma bn is convergent if a plus 1 is greater than 1. That means when a is greater than 0. Okay, so yeah, we can say that when a is greater than 0, the series is convergent. So converges if a is greater than 0. That's it. 68. Well, 69. A sequence is given as Tn is equal to 1 by n times 1 plus 1 by root 2 plus etc plus 1 by root n. That is actually that question is a simple question, but when you see the problem, it seems to be really tricky, and you may not get an idea how to start with. Okay, so the question is about the sequence Tn as well as the series Tn. Okay, so first let's go for the sequence. Okay, and we know that it's all about you can see all these like 1 plus 1 by root 2 plus etc plus 1 by root 10. It seems to be a partial sum, right? It seems to be a partial sum. So you take 1 by root 10, you take the sequence 1 by root 10, you know that that goes to 0, right? As n goes to infinity, that converges to 0. So what is the Cauchy's theorem for this sequence? Cauchy's theorem says that the sequence of arithmetic mean of the sequence, right? The sequence of the arithmetic mean of the sequence converges to the same limit. That is what the Cauchy's theorem says. So the arithmetic mean of this sequence is 1 plus 1 by root 2 plus etc plus 1 by root 10 by n, and that is nothing but Tn. See, so actually Tn is given in a tricky way. That's it. Okay, so uh, yeah, when you understand that, it's really simple, right? So that is Tn, and that converges to the same limit as of 1 by root n. so it converges to 0, right? Okay, so sequence Tn converges to 0, so B and D are false. Okay, now it's about series Tn. That's easy actually. uh, Easy in the sense, yeah, you take this 1 by n as some sigma an, okay, and try to apply the limit comparison test. Okay, so limit n tends to infinity Tn by an, this 1 by an 1 by n will be cancelled, and this is what you will get. So limit n tends to infinity 1 plus 1 by root 2 plus etc plus 1 by root n. Okay, and this is nothing but series 1 by root n, right? Series 1 by root n. Yeah, we write that as a partial sum. That's it. This is series 1 by n, 1 by root n. And 1 by root n means it's a p series, right? That is, it's 1 by n to the power 1 by 2. And this value is less than 1. So this one is a divergent series, right? So sigma n is equal to 1 to infinity, 1 by root n is equal to infinity. Okay, so in the limit comparison test, we got the limit as infinity, right? So actually, if it's a finite time, definitely, both the series behave alike. That is what the theorem says. But just below that, there is an additional condition. In case if you get this limit is infinity, you go for the individual sequences, the sequences in the numerator and the sequences in the denominator. All right. And if the sequence in the denominator diverges, okay, sequence in the denominator, here it's an actually, so the sequence in the denominator diverges, then that actual sequence also diverges. Such a theorem is there. Just go through that statement. It is just in your note, it is just below the uh, limit comparison test, it is written there. So we apply this one, and clearly sigma Tn diverges. So the answer is C. The series diverges and the sequence converges to 0. Right? Yeah. Okay, in question number 72, series are given. This series actually, I'm not going to explain this in detail, but just give you an idea. That's it. The first one, just take the limit, and you will get the limit as 1 not equal to 0. So the first series diverges. And in the second case, numerator is the second degree one, denominator is the third degree one. And from the denominator, so you take one n out, okay, and choose bn is equal to 1 by n, and apply the limit comparison with this 1 by n, so that you will get a finite limit. Okay, and we know that here sigma bn is a harmonic series that diverges, and therefore sigma n also diverges. So both of this series diverges. Okay, both S1 and S2 diverge. D is the correct option. All right. Well, in 71, root n by x to the power n root of n square plus 1. See, actually, I've told you this one is also a the convergent based on the values of x, right? In such cases, actually, we don't know the value of x, right? It can be positive, it can be negative, whatever. And here specifically, it's given that x is greater than 0. But still, you go for uh, absolute convergence using ratio test. Okay, as in the case of power series. Okay, because usually in the power series, x to the power n comes in the numerator, but here we have x to the power in the denominator. Okay, so that makes only a slight difference when you apply the ratio test. Okay, so that is the idea. You take an and an plus 1. All right. uh, I think I need to give you only the idea right now, right? Because however, you have to try all these questions yourself, right? I'm keep on saying the same thing, all right? Okay, so just apply the ratio test. So all these, the simplifications and all such stuffs, uh, that's really easy, I think. Okay, and here again, when you simplify, this is what you will get anyway. 1 by mod x, this is what you will get. Okay, so the simplification part is up to you. You try this. In case if you have any questions, we will discuss in the live session. All right, so it's 1 by mod x. So this must be less than 1 to get the series convergent, right? So sigma an converges when 1 by mod x is less than 1. 1 by mod x is less than 1 means, when mod x must be greater than 1. Mod x must be greater than 1. And so we have, actually, the x value, it's from 0 to infinity. It's given that x takes the value just greater than 0. Okay, and there we got, when mod x is greater than 1 and this is 1. So when x is just greater than 1, here it's convergent. Okay, and from 0 to 1, here it's divergent. Okay, now the question is, what happens at x is equal to 1? That also has to be checked. At x equal to 1, what happens? Okay, so that has to be checked separately. So when x is equal to 1, that case has to be checked, and no need to check for the negative values. Okay, because it's given that x is greater than 0, so that part simply uh, could be avoided. So sigma n is equal to sigma root n by root of n square plus 1. All right, and yeah, when x is equal to 1, this is what you will get, right? So take out an n from the denominator, and this is what you will get. And root n and this one will be cancelled. Okay, so you take sigma bn as 1 by root n. Okay, when you take the what the limit comparison test, okay, you will get a finite quantity there, and this series is divergent. Sigma bn is divergent, as it's a p series where p is equal to 1 by 2, which is less than 1. It's divergent. So sigma bn is divergent, so sigma n is also divergent. Okay, so when x is equal to 1, again it's divergent. Okay, so it converges only when x is strictly greater than 1. Okay, so converges for x is greater than 1 and diverges for x less than or equal to 1. A is the correct option, and all the other options are wrong. All right, so whenever you see that x to the power n either in the numerator or in the denominator, go for the absolute convergence and apply the ratio test. Okay, then you will get a clear cut idea. And in ratio test, there is a possibility that equality comes, right? That means when something is equal to 1, the test fails. So that case has to be dealt separately. Okay, yeah, that's it. So that's all about 71 and 72. Question number 72, it's like using central limit theorem evaluate. Actually, central limit theorem, it's actually this topic was there in the previous syllabus of JAM. So right now we are not going to discuss that central limit theorem. Okay, so I skipped this problem right now. Okay, uh, probably uh, yeah, we skip this problem 72. Okay. And in question number 73, that's also simple, I think, because we have two series, 1 by k plus 1, k plus 3, and here we have 1 by root of k plus 1 and root of k plus 3. Uh, yeah, only a little bit of rearrangements of the term is required, and you can go for what? You can go for a limit comparison test. Okay, so the ideas behind these two problems are limit comparison test. See, actually, if both numerator and denominator are of polynomial functions like algebraic functions, okay, then you can go for a limit comparison test. So apply limit comparison test here. So you can take out k from both the terms in the denominator. So you'll get k square and take sigma b as 1 by k square. Just divide and you'll get the limit as 1. Since this series converges, this one also converges. Okay, I am not going into the detail of this problem. In the same way, S2 also. can take out k from that, and you will get 1 by k out. So sigma bk is equal to 1 by k, and we know that this one is divergent. So when you apply the limit comparison test, you will get a finite quantity, and therefore since sigma bk diverges, s2 also diverges. So s1 converges and s2 diverges. B is the correct option. All right. And in 74 is a very simple question actually. It's like 1 plus 1 by 1 factorial plus 1 by 2 factorial plus etc plus 1 by n factorial. It seems to be a partial sum, right? So as n goes to infinity, what happens? As n goes to infinity, this is what you will get: 1 plus 1 by 1 factorial plus 1 by 2 factorial plus etc. And that is actually the series 1 by n factorial. N is equal to 1 to infinity. No, n is equal to 0 to infinity. Yeah, n is equal to 0 to infinity. Actually, this is nothing but e to the power 1, the standard expansion, right? You go for the expansion of e to the power x, and where you put when x is equal to 1, you will get it's e to the power 1, and that's expansion of that. Sigma 1 by n factorial is e. So yeah, the answer is e. So Sn converges in q. E is an irrational number, right? E is irrational. E is irrational. So you cannot write that as a rational number p by q. It's not possible. So the first option is wrong. That's it. Yeah, it converges, right? So definitely it's a Cauchy sequence, but does not converge in Q. Yeah, right. It does not converge in Q. So that is a correct statement. The subsequence is convergent in R. Yeah, because the sequence is convergent, so all its subsequence will be convergent. That's what a theorem in sequences we have seen. Okay, and here it's given that only when k is an even natural number, and that is wrong. Why? And that is wrong, right? Because any subsequence, whatever it is, every subsequence of a convergent sequence is convergent. Okay, so that is wrong since the statement only when k is an even natural number. Okay, even if k is not an even natural number, still that subsequence will be convergent. That's it. It's a convergent sequence, so it must be Cauchy. Fourth option is also wrong. That's all about 74. Okay. Question number 75 is yeah, I would say it's a series containing three unknowns A, B, C, right? So for what values of A, B, and C described in all these four options, the series is not convergent, and that is what the question says. So we have four different options given here, so we have to check all these separately actually. So it seems to be a big problem. Okay, so let's take the first one without assigning any of the conditions. Let's see what happens for the sequence. Okay, so always it's easy to assess as there is a to the power and n to the power b. Okay, log n is there, but still we go for what? Ratio test. Okay, ratio test. So a limit n goes to infinity, un plus 1 by un. You take the n plus 1th time by the nth time, and this is what you will get, right? And you take because the value of a is also not known, so always go for absolute convergence. Okay, so take the modulus of that. So mod a all to the power n plus 1 is there in the numerator, and mod a to the power n will be there in the denominator, and that will be cancelled, and you will get a mod a. And n to the power b and n plus 1 to the power b. See, both are having the same degree polynomial, and the leading coefficient is 1. So when you take the limit of that, you will get 1. We have seen many such problems. Okay, so directly you can write that limit is 1. Now the only problem is with this one, log n by log n plus 1 all to the power c. How can we find the limit of this one? And that's a question. Okay, so what we do is we take the corresponding continuous function log x by log x plus 1. Okay, so log x is a continuous function, log x plus 1 is also a continuous function, and you take the limit as x goes to infinity. X goes to infinity, so log infinity is infinity, and log this one is again going to be infinity, so infinity by infinity. Infinity by infinity is an indeterminate form, but it is an infinity by infinity function. Okay, so we go for L'Hospital rule, as the numerator and denominator are both differentiable functions. Okay, so we take the derivative of the numerator, so you'll get 1 by x, and here you'll get 1 by x plus 1. So as x goes to infinity, you'll get 1. All right, so this limit is going to be 1. So when you apply the what ratio test, you will get modulus of a. Okay, and interestingly, in the result there is no term of b and c, and that is independent of b and c, right? So directly we can say that, so if mod a is less than 1, that is what the ratio test says. If this limit is less than 1, sigma un converges, right? So if mod a is less than 1, sigma un converges. That's of clear, there is no doubt in it. Okay, for whatever be the value of b and c. Okay, so the first option is wrong then, because mod a is less than 1 is enough to say that the series converges. We need to get the values of a and b where it's not convergent. Got it? So the first option is wrong, because whenever you see mod a is less than 1, the series converges. Okay, so first option is wrong, and go for the second option. Okay, so and here the problem is, what happens when mod a is equal to 1, right? If mod a is greater than 1, again we can say that it's divergent, but unfortunately such an option is not here. Okay, so if mod a is equal to 1, what happens? That is the next question, and you know those options are given in different cases. So if a is equal to 1 and b is greater than 1, b is greater than 1, and c can be any value, right? Okay, so here again what you can do is, okay, you just write a is equal to 1, b let it be any value. Okay, I'm not giving you a particular value for b, so b is just greater than 1, so it's n to the power b. This is our series, then a becomes 1. Okay, log n to the power c, uh, log n to the power c. Okay, so here what I do is, I go for condensation test. I have told you once, that is something like log n all to the power something is there in a term. Condensation test will simplify that logarithmic term. So I go for the condensation test here. So I take un as 2 to the power n, a 2 to the power n. Okay, so it's 2 to the power n times, just replace all n by 2 to the power n. So you'll get here it's not like n, but it's bn. It's bn log 2 to the power n all to the power c. Okay, so you will get it's like, this is what you will get. I'll write it like this. It's 2 to the power b minus 1 times n. Okay, and n to the power c log 2 to the power c. Okay, and in this time you apply ratio test. Okay, you apply ratio test here. Actually we need to check the convergence of sigma un, and this is that sequence. So apply the ratio test here. So limit n goes to infinity, un plus 1 by un is equal to limit uh, un plus 1. So this is going to be, yeah, the power of 2 needs to be simplified as, the denominator it's the same like b minus 1 times n plus 1, and here it's b minus 1 times n. Okay, so when you simplify, and here what happens is, this 2 to the power b minus 1 n will be cancelled from both numerator and denominator, and here you will get it like 1 by 1 by 2 to the power b minus 1. See that? second. Okay, here it's the value of b is must be, what the value of b is greater than 1, it's given, right? So what happens is b minus 1 is greater than 0, right? Since b minus 1 is greater than 0 means this one always a quantity which is greater than 1. 1. So what happens is this must be less than 1. Okay. So by ratio test sigma un is convergent. Okay. Since sigma un is convergent, the given series is also convergent by condensation test. Okay, so that is what our idea is. So for the second case also, the whole whatever be the value of this one, it converges. If these conditions are satisfied, the series will be convergent. Okay, so that is wrong. And the third case, you put a is equal to 1 and b is greater than or equal to 0 and c is less than 1. Okay, and there simply I take some values here. If b is greater than or equal to 0, I put b equal to 0. Okay, I put b equal to 0 and c is equal to minus 1. So what happens is that it remains only the terms of log n, and even when c is less than, when c is a negative quantity, that goes to the numerator. So sigma log n, definitely it's divergent, right? So 3 is possible. That means there exist certain values in this region where the series is not convergent. So 3 is a correct option. And you go for a is equal to minus 1. You put a is equal to minus 1. When a is equal to minus 1, I am not going to give any value for b and c as it is. Okay. And here actually this is an alternating series then when a is equal to minus 1. And you go for Leibniz test here. As you know, as n goes to infinity, this one will go to 0. As n increases, this one is a decreasing sequence. So both of the conditions of Leibniz test will be satisfied and this series is convergent. Okay, so yeah, so the fourth one is always a convergent series, so that is not an option. So only option 3 is correct. And this one, actually the difficulty level of this problem is not that much, right? We can do this problem, but it will take more time because all these options have to be dealt independently. That's the thing. So it's a time consuming problem. That's all the thing. And we have okay, we'll do one more question, and question number 76. Okay, and that is simple actually. An is given as n plus 1 by n, and let's see what is this series. Minus 1 all to the power n plus 1, a n plus 1 n factorial. So an is this one, so a n plus 1 is going to be n plus 1 plus 1 by n plus 1. Divide each term by n factorial. So you'll get 1 by n factorial, n by n factorial, and n by n factorial, 1 by n factorial, 1 by n plus 1 times n factorial is n plus 1 factorial, and n by n factorial, you can cancel one n there, so you will get 1 by n minus 1 factorial, and you multiply each of these by minus 1 all to the power n plus 1. So you'll get three different series. Expand that, you can see that the first one is the first one, let it be there. The second one is the formula of e to the power minus 1. The third one is again e to the power minus 1. Okay, because this is what the sequence 1 minus 1 by 1 factorial plus 1 by 2 factorial, etc. This is e to the power minus 1. If you multiply that with a negative, you will get minus e to the power minus 1. And then 1 minus, we have the first time 1 minus 1 by 2 factorial. From here to here you have to select. That is going to be minus e to the power minus 1 plus 1. Okay, and that is this. First, second and third. Simplify that, you will get e to the power minus 1 plus 1. E to the power minus 1 plus 1. E to the power minus 1 plus 1 is the fourth option. Yeah, that's it. So that's it for this session. Okay. Yeah, bye. Take care.